Hi, and welcome back to the video series on deephaven.learn. In the previous videos, I've covered the basics of deephaven.learn, all the way from its design to real-time applications. In this final video, I'll solve a real-world problem brought to Deephaven by one of its users. Unlike code I've covered previously, this code is not a part of any of our how-to guides. It can, however, be found in a GitHub repository, for which I've provided the link in the description below. Unlike my previous videos, I won't be strictly following a script for most of this. I'll be going step by step through the thought process of using deephaven.learn and coding up a solution. As a result, this video will be longer than the previous ones in the series. But hopefully, you'll learn a thing or two not just about deephaven.learn, but about using Deephaven for data science in general. So without further ado, let's jump right into it. I'll be writing code that will perform Bollinger Band analysis on a feed of stock data. Deephaven's original use case is for financial analysis, so it seems fitting that you can perform it with deephaven.learn. As we'll see in a bit, this is a data science problem that requires some knowledge of Deephaven, Numpy, and a little bit of statistics. A user wants to perform Bollinger Band analysis on a table of stock prices. This table of stock prices has many unique stock tickers, as well as OHLC price data for each one. I'll be performing analysis using the closing price. Bollinger Bands are a measure of volatility in finance. They give indication of stability by calculating a moving average and a standard deviation of a given stock, option, derivative, or other financial commodity. In the case of this problem, we wish to calculate the Bollinger Band values for a given time window provided that at least n of the prices are valid in the window. Bollinger Bands are used all over the finance industry. In the case of Deephaven, they could be used in automated trading, machine learning, or a variety of other applications. A user may wish to monitor volatility for a minute, hour, day, or a week's worth of trades. Each window length provides a unique view of volatility that can be used as the basis for downstream decisions by an automated trading system. The solution will be as follows. For each unique stock in a table of stock trades, we will need to keep track of a moving window of the previous n trades. Trades with phony data, such as nans or negative values, must be ignored. For each moving window, we will calculate the mean and standard deviation. Those values will be used as our Bollinger Bands of volatility. Here I have a Deephaven session up and running. I have 4 panels in my GUI here, and I have removed myself from the bottom right corner because I will be scripting up the solution here in the bottom right, so I don't want my face to get in the way of what you can see in the code. So with that said, I have 4 panels up in this Deephaven session. The bottom left is a script that will write 1 row per second to a table that contains some randomly generated closing price values for a set of 5 random tickers. And those tickers will be letters A through E, and this happens once every second for 1 minute. If I run this code, we'll see a table pop up, which I'm going to move to the top right corner, so it's easily visible. And we can see here that this table has 4 columns, and is growing by 1 row every second. Now, the 4 columns are as follows. The millis column contains a timestamp in milliseconds. It's the current timestamp. You can see this going up by about 1. These are milliseconds, so this particular triplet here, the second to last one, is the current time in actual seconds. Up next we have our ticker, which can be anywhere from A to E. Next we have the close values, which are a random number between 10 and 100 with a 15% chance of being written as null. And then lastly we have the ticker index, which is just an integer number that corresponds to the order in which the tickers are written. So in this case, A is written first, A gets a 0, C is next, C gets a 1, D is number 2, E is 3, and then the last one to be written is B, we can see here is 4. And because these are written randomly, the tickers rather, every time we run that script, there's a good chance that we're going to get them in a different ordering, and the ticker index is going to change for each ticker. So with that said, let's go ahead and start coding up the solution. So I've discussed pretty extensively in my previous videos the helper functions, as well as the model function and the learn function call. So let's start up by coding up the helper functions. I'm going to start with my gather functions. And so in this case, let's take a look at our table. We want millis, close, and ticker index. We don't need the ticker. So for millis, we want that's a double. Close is a double, and ticker index is an integer. So we're going to need two gather functions, one for doubles and one for integers. So we're going to call the first one table to numpy double. It's going to take rows and columns. Return gather.table to numpy 2d. Rows, columns, and d type. It's double in this case. Up next we have table to numpy integer, which I'm going to call table to numpy int, and it's going to take the same arguments as table to numpy double, and the only thing this is going to do differently is it's going to specify the data type as 32-bit integers instead. So there are gather functions. For scatter functions, we're actually going to want more than one here. Because we're going to be returning a Bollinger Band, which consists of a mean, an upper band, and a lower band, we're going to want an individual scatter function for each output. Now we have 3 output values, so we're going to assign them right now to a particular index. So let's start with numpy to table, and this one's going to be for our mean. So this is going to take data and an index, and we're going to say that this is going to be the 0th value in the array we return. And we don't need to worry about this particular index here. We're going to return this as a one-dimensional NumPy array. And then next we're going to do table of NumPy to table lower bound. And we're going to return the lower bound next. And then we're going to do NumPy to table upper bound. Return data 2. Okay, so we're going to have 3 return values from this. Next, we're going to create our model function, which in this case, we're going to call Bollinger Band, because that's what we're doing, is we're calculating Bollinger Bands. And so we have 2 gather functions here. We have one for doubles and one for integers, so we're actually going to get 2 input values to our Bollinger Band function. We're going to get an array of doubles and an array of integers. And for now, let's just put pass here so we can code up the learn function call, which comes last. So we have our learn function. Let's just start off by not returning anything. We just want to make sure that we have the data throughput set up and working. So our learn function, we're not going to return anything at first, so there will be no output value. So we have 5 arguments required for the learn function call. We have table, we have model func, we have inputs, we have outputs, and we have the batch size. So let's go through each one of these individually. The table, first off, we see the table up here we want to work with is called T. Up next we have our model function, which is going to be Bollinger Band. Our inputs, we have 2 inputs that we want to work with. So let's do that. So we need a list, or an iterable, any iterable. A list is easiest. So the first one we're going to have is a learn.input object, and each learn.input object takes 2 arguments. The first argument is going to be your set of columns that you want this input object to consist of. So remember, we have 2 double columns and an integer column. Let's start out with our double columns. We have millis, and we have close. Okay, and then next we need to specify as the next argument, so the first argument is a list of columns. The second argument is our gather function. So we have table to numpy double. And then next we have another learn.input object, which is going to be our ticker index column. And because I only have 1 column here instead of 2, I don't need to pass. So I pass the first argument to this first learn.input object is a list, but because I only have 1 column here, that's not an iterable. It doesn't need to be a list. And then I have table to numpy int. Okay, so we have our inputs. Outputs, we will populate this in just a little bit, but for now we're going to say none because we just want to make sure that we get the data throughput set up properly. And then for a batch size, we're going to choose 1 because as this runs in real time, we're only receiving 1 new row every second, so a batch size of 1 is fine. And even if we let the table grow and call this on 60, it will still just do it 1 at a time. So let's make sure the data throughput works by printing out the data as we receive it. And if we run this, it should work, and we should see a bunch of printouts. All right, so great. So we can go scroll back up here, and we're going to come up to an important concept for this particular problem. So each time, because we have a batch size of 1, each set of 2 printouts corresponds to 1 learn function call. So the first time we print something out, we print out the double data. So we're printing out, the first time this gets called, the first row of the table T of the millis enclosed column. So for millis, we can see 1.648 whatever times 10 to the 12th. That corresponds to this value. And then we have 7.5 times 10 to the first. So we have $75 closing price at first. And we can see that the ticker index here is 0. Okay, this printout is the ticker index. Up next, we do it on the first row in the table, or rather the next row in the table, so this one. In this case, we have another timestamp, which is 1.64 whatever times 10 to the 12th. And then next, we come up to something important. So I mentioned previously that there's a 15% chance that the closed column gets written as a null value. That null value is actually this null double from the conversion utils module. And null double is a placeholder value which corresponds to the maximum negative number that a double value can hold in memory. So because it's a 64-bit number, the maximum value it can hold is about 1.8 times 10 to the 308th power, negative in this case. So anytime deephaven sees this number in memory, it actually just writes it as a null. So that's kind of important because in a deephaven table, you'll see an empty column here, or an empty cell in a column, but when we pass that into Numpy, it gets represented by this number instead. And then we get, for this second row here, we have a ticker index of 1, so we see 1. And this happens 60 times up until we get to the last row of the table, where we get a price of $80.87, represented here, and we get a ticker index of 2, shown here. So we have the data throughput working properly, which is great, because that's an important piece of the puzzle. Let's next, we need to actually put together our model function that will calculate the Bollinger Band values. And so let's start out by defining some globals, as well as our windows that we'll be keeping track of this stuff with. First off, we have a certain number of unique tickers in this table. In this case, it's 5. And then we want to specify how many valid trades we want to keep track of in our table. So let's just say that we want to keep track of the 5 most recent valid trades. Now, for this particular table, we write 1 row per second. There's 5 unique tickers, and the tickers are chosen randomly. If I come over here, current ticker is so we have a list of letters here, and then the current ticker is chosen as a random value, a random element from this array. So it is random, which means that there is an equal probability of any given one of these being chosen. So you could expect, on average, to receive 5 new closing prices for a given ticker every 25 seconds. So we're going to set the time window in milliseconds, because we're working with milliseconds here in this column, to, let's say, 30 seconds. And we choose 30 because it's likely that we'll get 5 valid trades in the last 30 seconds, given the parameters of the table that is updating in real time. So those are the global variables we need. We next need to define our windows. So for our windows, we need an individual window for each ticker in the table for the price and the time. So we will maintain 2 sets of windows. So the windows in particular, we're going to have windows of prices and windows of times. And so what we want is we want to fill it with negative values because later on down the line we're going to check to make sure values aren't negative, and we're going to use the numpy.ones method to construct a two-dimensional NumPy array full of basically bad data at the start. So we want n trades, n tickers, and we want to specify the data type to be doubles because we're working with doubles for the millisecond column and the close column. And we're going to do the same thing here. And so just to reiterate, if I run all of this code, we will see when I print this out, we'll see we have a 5x5 NumPy array. I just want to cover what each row and column in this NumPy array is going to represent. In the case of price windows, and the time windows rather, each individual row is going to correspond to a unique ticker. So in the case of this particular table here, the first ticker that gets written is A. So this first row is going to be for ticker A. Next we have ticker C, so this is going to be for ticker C. And then ticker D, E, and B. So we have ticker D, ticker E, and ticker B. And then each column is going to represent a previous observation. So the most recent will be stored all the way on the right, and then moving to the left to the fifth most recent. And we'll maintain this by rolling these windows in a circular fashion, and then replacing the value at the end anytime we receive a new observation that's valid. And so I'll get to that in just a second. So with that out of the way, we're going to actually start to fill our Bollinger Band model function with some real code. First and foremost, I have some global variables that I want to make sure I have access to in my Bollinger Band function. So I have global, time, windows, price, windows. Now, I have access to those, or at least I know I do for sure. Next, I want to split up my input data. So I have double data and int data. I know that both of these are going to be two-dimensional NumPy arrays, and I know that double data, because my batch size is 1 and I'm using 2 columns, I'm going to have 2 columns and 1 row in double data, and I'm going to have 1 column and 1 row in int data. The first column, this value, is going to correspond to the current time in milliseconds. Okay, and then the price, the closing price, is double data 0, 1. And then in a similar way, since our int data has only 1 value, I'm going to use the item method, so int data.item. And this is a method that NumPy has that says extract a value from an array that only contains 1 value. So I can say sim index, which is short for symbol index, is int data.item. So now we have the data that we want to work with, and what we want to do is start checking to make sure it's valid. So the first thing we want to check is the price valid? And in order to check for the price being valid, we have 2 conditions. We have number 1, is the price greater than 0? And number 2, is the price not a nan? So if price and price greater than 0, and this first check, if price, that just means is this an actual number? And does it exist? And then if price is greater than 0, just says ignore anything that's negative. And this is the reason why we fill initially these windows with -1s, so that if the price is less than 0, we're going to ignore it. Additionally, for sake of timekeeping, when we set the time windows full of -1s, these millisecond values are in the range of 10 to the 12th, whereas we're checking a time window of 3 times 10 to the 4th. So anytime the price window or the time window contains even a single -1 value, when we check the last minus the first, we're going to get something in the range of 10 to the 12th, where that's obviously going to be much larger than our time window. So it'll make our time checking nice and easy. Anyway, back to this. So assuming our price is valid, we then want to roll the data into one of these windows. And so I want to show what the rolling looks like with just a placeholder. So let's say A equals NumPy array 1, 2, 3, 4. Okay, so we have now an array called A, which contains the numbers 1, 2, 3, and 4. So I want to use NumPy's roll method. Okay, and so NumPy's roll method will take two arguments. It will take an array that you want to roll. In the case of a one-dimensional NumPy array, you don't need to specify an axis, and we're going to code this up so that we don't have to specify the axis in our script down here. But if I say numpy.roll, the second argument that you need to pass it is a number, and that number is an integer number that corresponds to the amount that you want to roll it. Now you can think of the number, it can be positive or negative. Positive corresponds with a left to right shift, and negative corresponds to a right to left shift. And as I mentioned previously, we want our most recent value to be stored all the way at the right. So what we want to do is push things from right to left, and then place the most recent value in at the end. So we're going to say we're going to roll it for -1, and we'll see here that when we roll -1, the 4 at the end moves 1 over to the left, the 3 moves over, the 2 moves over, and then the 1 that was all the way at the left over here actually gets circularly shifted all the way to the right. Now, for sake of our application, the 1 was previously the last value we wanted to keep track of. When we receive a new value, the 1 moves out of the window that we care about, and we can then replace this final value with our most recent observation. That's exactly what we're going to do. So we need to do this for both the price windows and the time windows. And so we're going to do it on a per row basis, and the row is going to correspond, or is going to be set by the symbol index that we read in here. Okay, so that says take that particular row, and we're going to do just what we did up here, is we're going to roll it. And then we're going to place the most recent observation at the right-hand side. And so this -1 means the rightmost value in our row. Equals price. And then we're going to do the exact same thing for the time windows. And there we have our shifting window operations happening. So the next thing we want to do is we want to calculate how much time has passed in our window. So we're going to say elapsed time equals time windows, the rightmost value in the row minus the leftmost value in the row. Okay, and then lastly, we want to check to make sure that the time window is valid. So the good thing about initially storing everything with a -1 is that anytime we have yet to receive 5 valid trades, there's going to be a -1 somewhere in the time windows. And you will never pass the time check if you have a -1 in there. So we don't need to make sure that there's 5 valid trades or trading prices here in this close column. We actually only need to check the time column at this point. So we say if elapsed time is less than or equal to n millis. And then here is where we will return what we want to return. And so we want to return 3 values. So first off, we need to calculate the mean and the standard deviation. So mean average equals numpy.mean. Price. We want to do it for the set of prices for this particular ticker. And then we want to calculate the standard deviation. Then we want to actually calculate the upper and the lower bound. So we have a lower bound equals average minus standard deviation, and we have an upper bound average plus standard deviation. Now the last thing we want to return is we want to return these as a numpy array. So return numpy.array. We want average, lower bound, upper bound, dtype equals np.double. Okay. And then we have to consider one final thing, which is what if we don't pass these checks? What if the price is invalid? If the price is invalid, we don't actually want to do anything at all. So we are simply going to return a numpy array full of null doubles. And I return 3 null doubles because in the case that we do pass the checks, this is a typo. In the case that we do pass the checks, we return 3 values. And in the case we don't pass the checks, we still want to return 3 values. Because remember, when we first constructed these scatter functions, we specified 3 of them so that we can return all 3 of the values. So the last step we need to take is we need to assign this a new table. We're going to call it T2 because our first table is T, and we're going to assign some outputs. So we need an iterable of learn.output objects. We're going to have 3 because we return 3 values. And for each one, we are going to set a column name. We're going to call this one the mean. We are going to specify the scatter function, which is numpy to table mean. And then we're going to specify the data type. For all 3 of these, the data type is going to be double. So then we're going to have lower bound, numpy to table lower bound, and double. And we have upper bound, numpy to table upper bound, double. So normally I wouldn't make a single line of code this wide, but I don't really feel like doing the formatting right now. But just to summarize, we have 3 outputs from our model. We have a single row output with 3 values. We want to get each value individually into its own column. So we have 1 scatter function return the first, 1 return the second, and 1 return the third value from that output data. And we assign each one its own learn.output object inside of this iterable, this list, where for each object we specify a column name, the particular scatter function that we specified for it, and the data type. Now, when I run this, it will hopefully work. I didn't make any typos, and it looks good, which is kind of a miracle. I make a lot of typos. And we see that we're starting to calculate some data here. We have a lower bound, an upper bound, and a mean. And so let's just check to make sure that this is actually working properly this happens for ticker C. So let's check just ticker C. So T2C equals T2.where, ticker equals C. And if we run that, we can check to make sure that we're only calculating Bollinger Bands for the correct value. So what we first want to do is check to make sure that we're not calculating Bollinger Bands for invalid prices. So our model appears to be ignoring this first one. So we have 1, 2, 3, 4, 5. So we calculate for the 5th value. We finally get some data here. And we want to make sure that it's within the valid time window. So again, this is in milliseconds and per seconds. So we have 888, and then we have this 412 here. That's the second value in seconds. So we have 412, we have 404. So that's a window of 8 seconds, which is obviously within 30 seconds. So this appears to be working properly. The last thing I want to do is I just want to have the where clauses that I typed up here, this one for a table full of the ticker C. I want one for each unique ticker in the table. So I want T2A equals T2.where. Ticker equals A, and I want to do that for all 5 of my tickers. And I will change these. And now when I run this, I'm going to try it on the live data and see what happens. And ooh, we get a bunch of tables. We can see T2 populating with our data. And once I start getting data here, I'm going to check to make sure it looks good. in the downstream table. So the first one we get is a calculation for the ticker E. Let's go to E, and that looks good. We have 1, 2, 3, 4, 5 before it starts calculating. It ignores a null, which is exactly what we want. We get valid data again, 993 minus 1, 2, 3, 4, 5. 993 minus 968 is 25, so that looks good. So by all indication, this is working properly. Now, keep in mind that I have already coded up this solution in the past, so I do have some prior knowledge of the problem. I'm doing this on dummy data and not a table of real trades, but I will say that this code does translate well to real-world stock trading data. This code runs pretty fast because it all uses Numpy. And I've already written a similar application for my colleague Amanda's Red Panda stock data application, and I do plan on including the code for that in the GitHub repository that is in the video description below. So with that said, this is how I coded up a solution to perform Bollinger Band analysis on a simulated a table of stock trades with some random elements to it, like random null values. So this is not an AI or machine learning problem, but it is a data science problem that does require some consideration. And this particular, the way that I solved this problem does translate well to AI and machine learning workflows in deephaven as well. So with that said, that's what I have for the demonstration today. This demonstration showed only one of the innumerable applications of deephaven.learn. It also showed how identical code can work on both static and real-time data for a real application brought forward by actual deephaven users. Bollinger Bands may be a simple financial analysis tool, but they're extremely useful and serve as the basis for much more complex analysis. This has been the final video in the series on deephaven.learn. I've covered everything you need to use deephaven.learn for your own applications, and I hope you found the series informative, interesting, and worthwhile. If you have any further comments, questions, or concerns, please reach out in the comments section below or through Gitter, GitHub discussions, or our community Slack page. The links for those last three can be found in the video description below. If you made it all the way through this video series, I want to thank you for taking the time out of your day to hopefully learn a few things from me. Check out deephaven's blog page, where I've already written a few pieces that use deephaven.learn and plan on writing many more in the future. And lastly, consider liking and subscribing for more content like this.